Hey guys, welcome back. This is going to be part 4 of the AP Physics C drag notes. So you have the notes that go along with this. Now consider the case in which there is no friction between the compartment and the track, but instead the compartment is brought to rest by a braking force that's negative kV, where k is a constant and v is the velocity of the compartment. Express all algebraic answers to the following in terms of m, r, k, v, subscript capital D and fundamental constants as appropriate. So for these, we want to make sure you use the letters that they tell you. So we're going to say that F net is equal to MA and negative KV is equal to MA, and I'm going to rewrite this as dV dt. And then I'm going to put the V and the dV together. And on this side, I would have minus Km dt and integrate this. All right, so they want us to solve this. So this would be minus K over M times T is equal to the natural log of V plus C. I don't remember, I need to go back a slide because I don't remember. I'm like a week removed from doing this problem. I don't remember if they gave us what the initial velocity is. I don't know what VD is. But I know that it's going to be from VD to V, right? And I can do this from 0 to T. So I have the natural log of V minus the natural log of VD, and I don't need to worry about the constant. I took a break from this. I was like a week ahead, but now I'm not, so I'm going back to this problem that I was in the middle of. All right, then I know if I subtract, it's the same as dividing, so this is going to be the natural log of V over VD, and then I can undo the natural log with E. So I'm going to have E minus K over MT is equal to V over VD. And so V is going to be equal to VDE minus K over M times T. All right, on the X below, sketch a graph of the magnitude of the acceleration of a compartment as a function of time. On the axis, explicitly label any intercepts, asymptotes, maximum or minimum with numerical values, algebraic expressions as appropriate. So my acceleration is going to be a maximum to start with because that's what I'm going the fastest, and this resistive force is going to stop it, and it's going to be a curve, so it should go down towards that way. All right, students are to conduct an experiment to investigate the relationship between the terminal speed of a stack of falling paper, coffee filters, and its mass. The procedure involves stacking a number of coffee filters like the one shown in the figure above and dropping the stack from rest. The students change the number of filters in the stack to vary the mass m while keeping the shape of the stack the same. As the stack of coffee filters falls, there is an air resistance drag force acting on the filters. The students suspect the drag force Fd is proportional to the square of the speed, where C is a constant. Using this relationship, derive an expression relating the terminal speed Vt and the mass m. Okay, so this would happen when these two are equal, right? So this would be C VT squared. I would do F net equals 0. I would have C VT squared equals mg, and I would have VT equals mg over C. The students conduct the experiment and obtain the following data. So I should break this down here. Assuming the functional relationship of the drag force above, use the grid below to plot a linear graph as a function of m to verify the relationship. Use the empty boxes in the data table as appropriate to record any calculated values you're graphing. Label the vertical axis as appropriate and place numbers on both axes. Okay, so we're saying that I want to solve this for m. So I'm going to square both sides. And I'm going to have C VT squared over G is equal to. What I want. So when I solve for G, that would be a linear graph, right? Mg over C. So I could have C VT squared over M is G, or they might do VT squared over M is G over C. This would be a constant, so it would give us a linear if this is our slope. All right, so I'm going to solve for VT squared here. And I'm going to write in what this is with units. So this is going to be worth points. Again, we have way more numbers there. You should round, right? Try to keep it similar to what you had to start with. All right. I'm going to take a picture of this so I can use it on the next slide. This would be appropriate use of. And then looking at this, this is going to be my y-axis. This is going to be my x-axis. All right, so I'm going to have VT squared, meter squared, second squared here, and I'm going to have m down here. Oh, they already put the m down there. And what I'm going to do with the m is I'm going to put times 10 to the negative third down here. So I only have to plot the whole numbers. And this goes up to a little bit more than 5. So if I go 1, 2, 1, 2, look at this. I should count it, huh? I thought the fifth one would be darker. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 2, 3, 4, 5, 6, 7. Yeah, every 5 I'm going to make 1. So 1, 2, 3, 4, 5, 1, 1, 2, 3, 4, 5, 2, 1, 2, 3, 4, 5, 3, 1, 2, 3, 4, 5, 4, 1, 2, 3, 4, 5, 5. And then my VT squared goes up to 1.12. And I have 1, 2, 3, 4, 5, 10, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5, 6, 7, 27. That's weird. So if I take 27 and I divide it by my biggest number, which is 1.12, get 0.04. So why don't I make it 0.05 each one? So that's going to make this 1, 2, 3, 4, 5. 0.25, 1, 2, 3, 4, 5, 0.5, 1, 2, 3, 4, 5, 0.75, 1, 2, 3, 4, 5, 1, 1, 2, 3, 4. And 1.12 is my biggest one. So, all right, now I'm just going to plot these. Stay up. So my first one is 0.26 and 1.12. My second one is 0.38 and 2.04. My next one is 0.67 and almost 3. Then I have 0.85 and 4.2, almost. That's right. And then I have 1.12 and 5.1. So it should be in the middle of here. And a little bit above that. All right, so I graphed this. Use your graph to calculate C. All right, so I need to do a best fit line and pick 2 points off of this. Yours is going to be much better than mine, hopefully. So I always circle in a big thing for the ones I'm using. Remember, you can't use your points, so I'm going to have 1.8, comma 3.4, and I'm going to have 5.2, 5.4, comma 1.1. So our y values is going to be 1.1 minus 0.4, and this is going to be meters squared per second squared. Our x value is going to be 5.4 minus 1.8. Remember, this is times 10 to the negative third, and that's going to be kilograms. This is not going to be our answer. I got 194 with the 4 repeating. But this is equal to G over C, right? So C would be equal to G divided by this. So I got 0.05. And given the the chance they're not going to, I guess I could have done it. Well, no, because they put mass on that thing. Very rarely is it going to be the slope if they get to choose what goes on the axis. It will very often be the inverse of the slope. All right, let's look at a particular stack of filters with mass m is dropped from rest and reached a speed very close to the terminal speed by the time it has fallen a vertical distance y. Sketch an appropriate graph of speed versus time for the time the filters are released up to the time t equals t the filters have fallen a distance of y. Indicate t equals t and a terminal speed vt on your graph. All right, so they're going to start from 0, and they're going to approach a speed that would be vt that's happening close to t. Suppose you had a graph like the one sketched in C that had a numerical scale on each axis. Describe how you could use the graph to approximate the distance y. I could take the area under the curve, right? So that would be the integral of the function of vt. And if they ask us, we can't take the integral of a function of vt, they said, how would we use the graph? I would have to take the area under the curve, whether it's approximating small boxes or if I can make it look. Determine an expression for the approximate amount of mechanical energy dissipated due to air resistance during the time the stack falls a distance y, where y is much greater than y. Express your answers in terms of y, m, vt, and fundamental constants. Okay, so we're starting with a certain amount of energy. And this is our total energy. And when it gets to the bottom, it's going to have energy that's equal to this, and then this part is going to make up the expression of how much we lost. So this air resistance is going to be a dissipation of energy, and so the work done by friction they want to call delta E. That's going to be equal to mgy minus 1/2 mvt squared. So this terminal velocity is going to be all the kinetic energy that I can get.